Hello to all fans of physics and physical experiments. This is Andrei Shetnikov with you. Today's video will be dedicated to adiabatic processes. And to start, I'll perform the following simple and interesting experiment. Here on the table, I have a thick-walled cylinder made of plexiglass. I'm putting a piece of cotton inside it. And on top, I insert a piston greased with oil, which fits tightly against the walls of the cylinder. And now I'm going to strike the piston sharply. So here we go. 1. And inside, a flame flashed for a very brief moment. It's better to watch this experiment filmed in the dark and with a high-speed camera. We're shooting at 480 frames per second. The entire process lasts 10 frames, which is 1/50th of a second. Let's slow the video down even more and we can see how the flame rises upward, following the piston as it shoots out. For the cotton to catch fire, the air needs to be heated to several hundred degrees, and we heat it up by rapidly compressing it. And why this happens, we'll figure out now, starting with a simple experiment in the AlgoDo program. So I have a box with a movable wall. Inside this box there are small individual balls flying around, representing molecules, and they frequently collide with the walls without losing any significant energy. Now I start slowly moving the movable wall, pushing the piston further inside the box. And with each collision, because the piston is moving, the energy of the colliding particle increases. Then it transfers this energy to other particles through collisions. In this way, the energy of the particles inside the box keeps increasing. And this means that we've raised the temperature of the gas inside the box. Actually, we've already considered the motion of a single particle inside a one-dimensional box with a movable wall in the video Adiabatic invariant, and I recommend you watch it. And of course, all of this could have been explained without drawing molecules, using macroscopic language. Here is our piston. We hold it in place with a force equal to the pressure of the gas times the area of the piston, P times S. Then we slightly increase this force. Well, practically it remains almost the same. And we slowly move the piston inward by a distance dx, doing work dA equal to F times dx. But if instead of F we substitute P times S, then S dx will be the change in volume. However, we need to put a minus sign here, because when we move the piston, we decrease the volume, not increase it. Now the most important thing, why is our process adiabatic? What does this word mean? It means that the gas inside, specifically the air located directly under the piston, does not exchange any significant heat through its surrounding walls with the external outside world. Well, in the particular case of our fire piston experiment, this phenomenon happened precisely because we pushed the piston in very quickly and with considerable force. And that's why all the work we did goes into changing the internal energy of the gas. That is, into increasing its temperature. And accordingly, we can write the equation for the adiabatic process. But the main thing to understand here, once again, is that an adiabatic process is one that occurs without heat exchange with the external environment. And of course, the main application of adiabatic compression is the preliminary heating of air in various heat engines. In a diesel engine, the air under the piston is compressed to such an extent that the fuel ignites on its own without a spark plug, and then the heated air expands and does much more work than was required to compress it. A conventional internal combustion engine essentially operates in the same way, but due to a lower compression ratio, the fuel mixture has to be ignited with a spark plug. And in an aircraft turbojet engine, adiabatic compression is achieved with the help of a compressor. Then the heated air, together with the combustion products, spins the turbine blades, rushes out of the nozzle as a jet stream, and the turbine drives the compressor and the fan, which generates the main thrust force.
And so Andrei talked about the heating of gas during adiabatic compression. It's clear that the process can be reversed, and during adiabatic expansion the gas should cool down. Let's return to our model in AlgoDo and slowly move the piston back. With each collision of a molecule with the moving piston, it loses part of its energy, and due to collisions with other molecules, this energy loss gradually redistributes among all the molecules, causing the gas temperature to drop. Look at how much slower the molecules are moving now. That was a computer model. And now we'll do a real-life experiment. And for the gas expansion to be close to adiabatic, it needs to happen very quickly, so that there isn't enough time for heat exchange to occur. Here in the holder, there is a small cylinder of carbon dioxide compressed to 60 atmospheres. Now what I'm going to do is carefully puncture this particular cylinder, right here. And now the screw is getting covered with frost. And the cylinder has become very cold, so it would be good to measure how much it has cooled down. In this experiment, we're using two thermocouples. One is attached to the neck of the cylinder, and the other is placed underneath it. A hammer strike, the seal is broken, and a jet of expanding CO2 rushes downward. Let's see what the temperature sensors showed in this experiment. The one placed under the jet cooled down to minus 40 degrees Celsius, and you can see that it would have kept cooling further, but the gas in the cylinder ran out. The one attached to the neck cooled down more slowly. The cylinder's heat capacity is too high for this experiment. Adiabatic expansion of gases is used to create low temperatures. In a refrigerator, the compressor forces the gaseous refrigerant under high pressure into the condenser. From being compressed, it heats up, releases heat to the surrounding air, and transitions from a gaseous phase to a liquid one. Then the liquid refrigerant passes through a narrow capillary tube. After that, its pressure drops, it evaporates, cools down, and absorbs heat from the food in the refrigerator compartment. Then the refrigerant returns to the compressor, and this cycle repeats. And it's important to understand that adiabatic processes can occur not only with gases but also with other substances. The main thing is that these processes occur quickly enough so that heat exchange with the surrounding environment doesn't have time to take place. And now I'm going to show you a remarkable experiment with this balloon. I will stretch it quickly and then let it go. At the same time, the temperature of the rubber will be measured using this contactless sensor, which has virtually no inertia and records the temperature without delay. Right now, the sensor shows room temperature, 26 degrees Celsius. I stretch the rubber sharply and the temperature rises to 38 degrees, 12 degrees above room temperature. Now the rubber is cooling down. Let's wait until its temperature gets closer to room temperature. There it has dropped to 27 degrees. I release the rubber and the temperature almost instantly drops to 15 degrees. That is again by 12 degrees. And then the rubber gradually warms up from contact with the air. So it turns out that rubber behaves completely differently from a gas. A gas heats up when compressed and cools down when expanded. But rubber behaves exactly the opposite. When stretched, rubber heats up, and when it contracts back, it cools down. And we need to somehow explain this. Here the structure of rubber plays an important role. It consists of macromolecules of rubber, each several tens of thousands of units long. In its undeformed state, each such molecule resembles the trajectory of a wandering Brownian particle. If a molecule consists of 10,000 units, its characteristic size is on the order of 100 units. When we stretch rubber, the molecular chains are extended in the longitudinal direction, while their size in the transverse direction decreases. The units of the molecules are in constant motion, and we will illustrate this with a simple model. Massive balls are connected into a chain, with the links able to freely rotate relative to each other. And each of the balls has some initial kinetic energy. A piston pulls on the end of the chain and does work against the stretching force of the rod attached to it. Due to this work, the kinetic energy of the system increases, and we say that its temperature rises, just as we saw in our experiment. Now let's return to gases and find out what the graph of an adiabat looks like in volume pressure coordinates. But first, let's draw the isotherm graph of an ideal gas. When we change the volume of a gas at constant temperature, Boyle's law applies, and the product of the gas's pressure and volume remains constant. So the isotherm graph is a hyperbola. I'll draw two more hyperbolas, one for a lower temperature and another for a higher one. And during adiabatic compression, the volume decreases, the temperature rises, and we move to a higher isotherm. Accordingly, during adiabatic expansion, the temperature drops and we move to a lower isotherm. That's why the adiabatic curve is steeper than the isotherm curve. In theory, it is shown that in an adiabatic process, the product of PV raised to the power of gamma remains constant. The coefficient gamma is called the adiabatic index, and it is always greater than 1. For an ideal monatomic gas, it is 5/3, and for a diatomic gas, it is 7/5, that is 1.4. Air consists mainly of diatomic molecules of nitrogen and oxygen, so its adiabatic index under normal conditions is very close to 1.4. Now let's do another experiment with this 5-liter plastic bottle. We will pump air into it using a pump, increasing the pressure to 1.5 atmospheres. There's also a temperature sensor inserted inside the bottle, which we'll use to measure the air temperature inside. I turn on the pump, and the air temperature inside the bottle immediately starts to noticeably rise. The ambient room temperature was precisely 26 degrees Celsius, and the air within the bottle has already heated up to a significant 32 degrees Celsius and continues to steadily rise. This demonstrates a clear and rapid thermal change. 34 degrees. You can hear that the pump is already having a hard time working. It's time to stop it. So due to compression, the air heated up by 8 degrees, and now it's giving off heat through the walls of the bottle to the surrounding environment. And we'll wait until the air inside the bottle cools down almost to room temperature. Now the air has cooled, and I'm going to quickly open the bottle cap. The pressure drops to atmospheric, and the air temperature in the bottle suddenly falls to 21 degrees, 5 degrees below room temperature. After that, the air will warm up from the external environment until thermal equilibrium is established. By the way, this experiment is similar to the one with rubber. In it, the air heats up during compression, and then in the stress state, thermal equilibrium is established. Then the air cools down as it expands, and once again thermal equilibrium is established. And here it should be noted that in our experiment, the compression of the gas was not entirely adiabatic, because when the pressure doubles from 1 to 2 atmospheres during an adiabatic process, the temperature should have increased by 20%. And if you take into account that room temperature was 300 Kelvin, it should have risen by 60 degrees, but in our case it only increased by 8. Nevertheless, a thorough understanding of the adiabatic process significantly helps us to clearly explain the comprehensive results of this particular experiment as well. And now it's time to move on to our traditional final question. And to ask it, I'll conduct one more experiment. Here, a little water and isopropyl alcohol have been poured into a 5-liter bottle. Now I'll turn on the pump and wait for the pressure to build up. And now the glass bottle is gradually swelling, expanding and tipping over to one side, slowly but surely. No worries at all. We will certainly hold it firmly in place, ensuring its stability. Meanwhile, the pressure keeps rising higher and higher. But we want to bring it up to 2 atmospheres, and we'll wait for that. And now the pump is already struggling to work. I stop it and open the cap. There's a sound like opening a bottle of champagne, and inside the bottle, a fog appears, filling it completely. So the question is, why did this happen? Share your thoughts about this in the comments under this video on YouTube.